So we just talked about pH, focusing on strong acids and bases. And if we see a calculation, whether it's free response or multiple choice, and it's a strong acid or base, we get excited because that's when the math is really easy. But it's way more common to be dealing with acids and bases that are weak and understanding their equilibrium. So weak acids and weak bases partially ionize or ionize in terms of an equilibrium reaction in which we have a significant amount of products and reactants. All weak acids and all weak bases ionize in the same general way. The acids donate a hydrogen, making a hydronium ion. The bases accept the hydrogen, making a hydroxide ion. And then we are left with different amounts of hydronium with our conjugate, with our acid and its conjugate base, or hydroxide with our base and its conjugate acid. And if this is all happening in water, we can set it up as an equilibrium and turn that into a K expression. The general formula for an acid would be a Ka, in which we look at the concentration of the ions over the concentration of the acid. In terms of Kb, it'd be the concentration of the ions over the concentration of the base. Water, being pure liquid, is left out of that. As it ionizes, there's a couple key things that are really important and helpful as we start to look at the math on this. But what's important here is that we have molarities for all of these, that we know how much weak acid we have, but that amount of weak acid does not turn 100% into hydronium ion. So I can't just take the molarity of my acid concentration or my base concentration in terms of weak acids and bases to find out the pH. I have to think of it as an equilibrium, and I have to think of it in terms of K values, and we'll even see a Rice table. But those K values are the way that I can quantify how strong or weak it is. We've talked about it in terms of molecular structure. We've talked about it in terms of conjugate acids and bases, what's stronger and weaker. But Ka and Kb are how we turn that into numbers. So we've got some sample equations and numbers down here. All of these you'll see are kind of specific versions of the two equations we looked up there as Ka and B. So instead of A minus as my anion, I could have the chlorite or the nitrite or the fluoride ion. Each of those gives me a different K value. And just like all K values, the bigger the value, the more shifted to the right, or the higher concentration, in this case, of my ions. So chlorus of these four has a higher K value, meaning it has more of it ionized and less of it still together. That would result for equal molarities in a lower pH. The nitrous is a little bit lower in terms of its K. Hydrofluoric's even lower. Formic is even lower than that. Sorry, hydrofluoric's a little bit higher than nitrous. Then notice that they were out of order on that. For the bases, I've got a bunch of values here. These look like they're in order, but we've got several different bases, and ammonia is a really common base. But there's also a lot of times what we would call ammonia derivatives, or a lot of things that are made of carbon, hydrogen with nitrogen snuck in there. Those are really common weak bases. So our weak acids are all of the things starting with hydrogen that aren't strong. Our weak bases, they're not as easy to recognize at times. But if you're going to see NH3 or something with N and H and then a whole bunch of carbon and hydrogen, that's really common that it is a base. Each of these things accepts the hydrogen, making some hydroxide over here. When we have a strong acid or when we have a strong base, you may see that it gives you a K value. It may say that it's much, much greater than 1. It may say that it's very large. But in general, they don't even give you a K. But that's a way that they can communicate that an acid we don't know is strong, that's not on our list, is strong. Any of those things there. So the other thing, and we'll talk about this a little bit, we've talked about polyprotic, and you've seen some K values. Each time we're just donating one hydrogen ion. So for that, you may see it as Ka1, Ka2, Ka3, et cetera, et cetera. And when you're doing that, each step becomes less and less common. Each step favors the products even less. So your Ka1's always going to be the biggest. That can also happen with Kb, and we've got some examples here with the carbonate and the bicarbonate ion. Because these are all in equilibrium, because we do have sorry, the K values for these, but more importantly, we've already established that it's in water, so we have some hydroxide or some hydronium. There's some important equations here that allow us to connect our Ka to our Kb, and that's based upon Kw. The acid is the thing that produces the hydronium. Well, it has a conjugate base that produces hydroxide. So that would be our Kb. The product of those two, we can put the equations together to prove this. We know that putting one K with another K, they get combined by multiplying. Well, when we do that with our acid and its conjugate base, the way the two of them act in water, they actually combine to make the Kw expression right there. And if at 25, we'll keep saying that as a reminder, it's 1 to the negative 14th, or 14, the negative log of this is the negative log of Ka and the negative log of Kb. Those are important things. The pKa especially, but also the pKb are numbers that we will be using as we're describing and understanding our different values.